In this week, we're going to be focused on interpreting the solutions we found as we solved systems of equations. In particular, the idea of the eigenvectors and the eigenvalues and what meaning they might carry in themselves that will help us understand the more general solutions. We'll start our analysis with a quick review. We have here a linear differential equation for x1 and a linear differential equation for x2, and they're interdependent. However, they're easy enough to write in our standard matrix form. The left-hand side is essentially the derivative of x1 and x2 stacked together. And if we put x1 and x2 in a vector here, we can separate the coefficients from the variables on the right-hand side. And that would generate the matrix here, giving us negative 3x1 plus 2x2, and for the second equation, 4x1 minus x2. So no change in information, simply a change in the way it's presented. We know from our work with systems already that to find the solutions to this differential equation, we're going to need to find the eigenvalues of A. And to do that, we set the determinant of A minus lambda I or Ri, your choice of variable. We're going to set that equal to 0. And that's 3, 2, 4, minus 1 is the matrix we started with. And the minus lambda I means down the diagonals, we subtract the variable we're looking for. Then we can compute that with the cross product multiplication process. We get minus 3 minus lambda times minus 1 minus lambda. And then we subtract the other product, the 4 times the 2. And that gives us 3 plus lambda plus 3 lambda is plus 4 lambda plus lambda squared minus 8. That's lambda squared plus 4 lambda minus 5. And we want that to equal 0. So we might go hunting for factors. And in fact, we can see one here. If we have plus 5 and minus 1, that'll give us the same quadratic we were provided with to start with. And so lambda equals negative 5 and positive 1 are the eigenvalues of the matrix A. As a side note, that means our solution will contain e to the negative 5t's and e to the positive 1t terms. Those are going to be the building blocks from the functions of our solution. To include the other details in the solution, we need the corresponding eigenvectors of A. And for that, we look at each of our eigenvalues in turn. We'll look at negative 5 first, arbitrarily. And then for that, we solve A minus lambda I times a vector V is equal to the 0 vector. This vector V is what we're looking for. In this instance, we're going to subtract negative 5, so add 5 to each of the diagonal elements. That'll give us 2 and 2, and 4 minus 1 plus 5 is also 4. And we'll call these two elements of V, V1 and V2. That has to equal the 0 vector. And we see immediately that these two rows are multiples of each other, so they're redundant. And so we get 2V1 plus 2V2 has to equal 0, or V1 is equal to minus V2. Then we get to pick one of the values. We'll pick V2 to be 1, and that means V1 will be negative 1. So our eigenvector for this eigenvalue, let's call it lambda 1, will be V1, which is negative 1 on top, 1 on the bottom. We could also have picked them the other way around. Either way would be fine. They would both be eigenvalues because they'd still be multiples of each other. And any multiple would still satisfy this equation. The second eigenvalue, lambda 2, would be positive 1. And for that, we set up our matrix again of A minus 1 on the diagonals. So we'll have negative 4 and 2, 4, and minus 1 again on this diagonal equals the 0 vector. And again, we see that duplication. So one of the rows is redundant. From this, we get negative 4v1 plus 2v2 must equal 0, or v1 is equal to 1/2 v2 by the time we rearrange that. For this instance, we're going to pick v2 so we get a nice v1. So we're going to pick v2 equal to 2, and that'll leave us with v1 being half of that, or 1. So v2 is the vector 1, 2. That will be the eigenvector corresponding to lambda equals 1. And that's it. It's a 2 by 2 matrix. We have 2 eigenvalues and 2 corresponding eigenvectors. Having found those eigenvalues and eigenvectors, we can immediately write down the solution in vector form. It'll be c1 e to the negative 5t times the eigenvector that went with that, which is negative 1, 1, plus c2 e to the 1t, other eigenvalue, and its corresponding eigenvector. Once we have those values, the solution is easy to write out. The last step is to interpret the results, though, because we didn't actually find, or we weren't actually asked, what is x of t as a vector. We were given x1 as a scalar function. Well, x1 of t is just the first row in this entire vector that's being generated here. So c1 e to the negative 5t times minus 1 plus c2 e to the t times 1. So we gather all the terms here, and when there's a vector, we grab the first element like so. To get c2, we take the scalars, but then we grab the bottom element in the vectors whenever we need it. So x2 of t will be c1 e to the negative 5t times positive 1, and c2 e to the t times 2. And aside from some tidying we might do with the ones and negative signs, we now have a formula for what x1 of t is over time. Our next step is to figure out what we might learn, not from this form here, which has all the details, but we kind of get lost in them, but more by looking at the eigenvalues and eigenvectors themselves and knowing how they fit into the solution. What can we learn from that?